Section 7.3 talks about polar coordinates. So here again, it's kind of putting a lot of things together. Now, if you go to my YouTube channel and if you check second semester calculus, not this one, there's another second semester calculus. It also has a thorough polar coordinate section. That'll be section, I believe, 8.3. Or if you go to my Math 8 trigonometry and you go to polar, that one takes this section and break it into two sections, and it's in actually, yeah, two sections, and it's broken down in full details. Here we're trying to kind of like remind you of what you already know. That's what this section is. In this section, there's nothing new besides what you should have learned in trig already, but I'm going to start from scratch, but we're moving a bit faster than we do in trig because the assumption is that I'm reminding you of this. Remember, if you're dealing with a coordinate point, instead of x and y, it's always r and theta, in which we rotate first. If r is positive, you move in the direction of theta. If r is negative, you move in the opposite direction. What does that mean? Recall the polar grid. The polar grid consists of a positive x-axis, but it's a ray, meaning it has direction already. You're already pointing in the positive x direction, or you're already pointing east. If you talk about 0 degrees, you're already pointing in this direction. So we rotate theta first. If r is, let's say theta is this much. If r is positive, I'm going to be somewhere here. If r is negative, I'm going to move in the opposite direction and be somewhere there. And if I look at the quadrants, well, that makes the difference between opposite quadrants. You know, any angle that lies in quadrant 1, that point could be in quadrant 1 or quadrant 3, depending whether r is positive or negative. Similarly, if the angle rotates to the third quadrant, if r is positive or negative, you end up being in quadrant 3 or 1. Same thing with those two. So to start off, a quick reminder of how this works. If I wanted to pinpoint that point in the following plot, the following whose polar coordinates are given, and then mark off the distance, and okay, just mark the point, 5 pi over 3, 5 pi over 3. So remember, I start pointing in the positive x direction. I'm going to rotate to 5 pi over 3. I'm going to rotate all around until I line up with 5 pi over 3. Now on your exam, I give you a grid. You have to label the points. Well, the grid would look like this. You have to label everything. Well, let's see how this works. In this case, if r is positive, I'm in this quadrant, but I notice that r is negative. So instead of moving again, I start pointing this way. As I'm rotating, it's kind of like a flashlight. By the time I stop here, I'm already pointing. The flashlight is already pointing in that direction. If r is positive, I move in that direction. If r is negative, I move in the opposite direction. R is negative 2. What that means, I'm going to go in reverse 2 steps, and I'm right there. And that's number 126. Now, looking at 130, I'm going to do 128 after. 5 pi over 6. 5 pi over 6 is right there. I'm going to rotate to 5 pi over 6. Now, I'm going to be along this path. If r is positive, I'm in quadrant 2. If r is negative, I'm in quadrant 4. r is positive 2. I move in that direction 2 units, and that is 130. And if I look at this, rotate to 3 pi over 4. 3 pi over 4 is right there. So again, I'm along this path. I'm pointing in this direction. Since r is negative, I'm going to move in the opposite direction. 1, 2, 3, 4, and I'm right there. All right. Now, again, this is really 3 sections combined into 1 section. So if you really haven't seen trig, or you've never taken trig, I strongly suggest that you go to my trig lecture in online and view right there. Look for the topics. View polar coordinates right there. 8.1. We start off with what I just mentioned, but we do a lot more examples. Converting back and forth, we're going to do that now. And then we talk about what does a point mean, converting forward and backwards. And then 8.2, we're going to also how to graph those. And we graph every possible scenario you can think of. And then that one you don't have to worry about. So you just have to worry about section 8.1 and 8.2 on my YouTube channel if you really need that much review. Here we're going to pick those two sections and combine them into one, and that's a lot of work. But the assumption is that you've seen this before. So let's talk about how to convert forward and backwards. By the way, if you are going to take the third semester calculus, I suggest you nail this section or the trig sections fully, because in third semester calculus, this comes back with another variable. And they say this is polar coordinates in 3 dimensions. And then they add to that also spherical coordinates, which is a bit more of a challenge of this if you're weak in trig. So this is your chance. Now let's move on. Given x and y, if I was given x and y, if I gave you a point for simplicity reason, let's say that's x, that's y. If you really think about it, there is x, there is y, those are given. So what we want to find r, well, obviously r squared equal x squared plus y squared. And we want theta. Again, given the purple, we know that tan of theta equal y over x. And that's all there is to it. Now, given r and theta, if I was to give you r and theta, and again, for simplicity reasons, let's say you rotated this much, and r was this much. So the difference between ray and this r is finite. It stops. It gives you direction, but it stops at a given point. Now, this is theta and this is r. If I wanted to find x and y, well, guess what? Given a right triangle where I have the angle, the hypotenuse, and I want the adjacent, cosine of theta is the opposite over the hypotenuse, the adjacent over the hypotenuse, and if I cross multiply, x would equal r cosine of theta. Similarly, if I have a right triangle given the hypotenuse and angle and the opposite, sine of theta is the opposite over the hypotenuse. If I cross multiply, y equal r times the sine of theta. So for this class, you really don't have to convert much, but for your next course, if you're gonna take the third semester calculus, you have no idea how important this is. I mean, I'm tempted to go and show you, but then this video will stretch a lot longer than I want. But you want to see tons more example than this, go to the review of trigonometry. And if not now, do it at least in the summer. Let's see how this plays. So this is given. What am I given? I'm given x and y. I'm given 2, 2. That point right there. 2 and 2. Well, what do they want? They want r and theta. Well, let's see. Obviously, now you got to be careful with this. R squared is 2 squared plus 2 squared. R squared is 4 plus 4, which is 8. Now be really careful. R equal plus or minus 2 radical 2. Now, I'm going to suggest, this is just me, just to make your life easy, I'm going to suggest that make R positive, you don't have to, and theta in positive rotation, you don't have to. Well, tan of theta equals the opposite over the adjacent. Tan of theta equal 1. That means theta is pi over 4. So if I was to write this as r and theta, I would say rotate to pi over 4 and move 2 radical 2. You will end up at the same location. And why would you need to do something like that? Because when you want to find the area under the curve, if you're dealing with arcs, it's better to use polar than it is to use rectangles, like an ellipse or a circle. This problem, again, r and theta, so this is x and y. I'm trying to figure out what r and theta are. Well, we're going to move 4 units to the right. 1, 2, 3, 4, 3 units up. There's the point. Well, think about it this way. I'm given this is 4, this is 3. To find the hypotenuse, I use Pythagorean theorem. I would say r squared equal 3 squared plus 4 squared, 16. So that's 25. Again, r could be plus or minus 5. I suggest, for simplicity reasons, choose r to be positive all the time and have theta rotate in positive rotation, because there's an infinite amount of ways you could list that point. We want the most basic one. And if I take tan of theta to equal the opposite over the adjacent, then theta is the inverse tangent of 3/4. And that is not a standard angle, but if I take my calculator out, and using radians will confuse you more, I'll show you really quick. This problem is in radians. If I take the inverse tangent of 3/4, most likely that will be the answer in the back of the book, 0.64, but if you convert that to degrees, it should make more sense, somewhat. There it is. Nope. Oh, it didn't click second. Okay, clear again. Second mode. Okay, there it is, 3. And if I click it again, it's really 36 point, almost 37 degrees. So rotate 37 degrees and move 5 in that direction. You end up being at the same location. Again, the book will never use this. The book will use the 0.65. They will always write this in radians. Not a big deal, really. Just a location. Now, if you're not allowed a calculator, you would leave the answer like that. That's the actual angle. And that's the radius. Again, there's an infinite amount of ways I could list that point, but let's make it as straightforward as possible. Now, can you go the other way around? The other way around turns out to be a lot easier, provided, again, you know your trig. So in this case, they're saying, look, rotate to 5 pi over 4. There's 5 pi over 4. Move 2 units. You're right there. So what's x and what's y? Well, we know that x equal r the cosine of theta. So x is 2 the cosine of 5 pi over 4. X is 2 times radical 2 over 2. In this quadrant, that's negative, so x equal negative radical 2. And y equal r sine of theta. Well, that turns out to be 2 times the sine of 5 pi over 4. That turns out to be 2 times negative radical 2 over 2, which is also negative radical 2. So that point right there is r and theta. In x and y, it turns out to be negative radical 2, negative radical 2. Move 1 point sum, you end up at the same location. Similarly here, no need to graph it. I could simply say, look, x equal. Graphing it saves you a lot of work, especially if it falls on one of those. X equal r, there's theta, the cosine of theta. Now let me show you where that point is, just to match. 3 pi over 4 is right there. Since r is negative, that's the location I'm trying to find. Well, x equal negative 3 radical 2 over 2. And 3 pi over 4 is right there. All students take, so cosine is negative. That turns out to be positive 3 radical 2 over 2. Okay, very good. So this is r and theta. If I want to write it in x and y, I know the x is already 3 radical 2 over 2. And I know that y equal r the sine of theta, y equal negative 3 the sine of 3 pi over 4, y equal negative 3, that's radical 2 over 2. But in this quadrant, sine is positive, so that's negative 3 radical 2 over 2, and it matches. This is saying move 3 radical 2 over 2 to the right, and down 3 radical 2 over 2, and you end up being at the same location. That's that. So this is as much review as I'm going to go with you as far as taking those in and converting back and forth or plotting points. Now a quick review of how this works. Hopefully, again, this is a review. If you know this, that's going to save you a lot of time. If not, I'm going to show you a way of how to pick up the graph from the basics. So I'm assuming you know how to graph y equals 6 cosine of theta, y equal 3 minus 2 cosine of x, if you recall these things. Now let's talk about this really quick. R equal A is, oh, everything's shifted. Why is that? Let's see, catch that. Oh. Okay, somehow I shifted everything. I'm not sure how, but it's okay. Now they're somewhat shifted back. Okay, not bad. Almost. I'm not picky, it's just important so you see really what's happening. And visually, you're going to have to pick up the solution off of that. No, not again. I don't need it to move forward, just this. Okay, let's see here. R equal A. Again, this has been derived. This is a circle centered at the origin with a radius of A. R equal A, the cosine of theta. Cosine is the x. So this is a circle that looks like this. Either one of those or one of those where the diameter is A. Now, if A is positive, then this is a circle with a diameter of A wrapped around the positive x-axis because cosine is the x. And if A is negative, negative 3, the cosine of theta, that means this circle is wrapped around the negative x-axis. Similarly with y, since that's y, it's one of those two circles. And again, with a diameter of A, if sine is the y, if A is positive, then you're wrapped around the positive y-axis. And if A is negative, you're wrapped around the negative y-axis. Now, if you happen to give it a shift, then again, B is the cosine. B being a cosine, that means the graph is wrapped around the positive x-axis. If B is bigger than 0, and if B is less than 0 and that's x, you're wrapping like a heart shape. It could be with a loop or without a loop. Again, we'll point that out. I'll show you how to get the whole graph from the actual basic graphs, but this helps a lot if you keep that in mind because of symmetry. So once I get the upper half, I know the bottom half looks the same. Similarly, if I run to this problem and say, look, what about the sine? Sine is the y. If B is positive, oh, this is if B is negative. If B is positive, it's a heart shape that's wrapped around the positive y-axis. It could have a loop, it could not have a loop. I'll show you when that happens. Or it could be wrapped around the negative y-axis. If B is negative, right? And lastly, something, this one you really need to remember. If I play around with the angle, so the sine of n theta, cosine of n theta. If n is odd, so we're talking about the sine of theta, 3 theta, 5 theta, and the list goes on, then you get that many leaved graphs. That number, you get 3 leaves, 5 leaves. If n is even. Whether it's sine or cosine, it doesn't matter. So we're talking about sine of 2 theta, sine of 4 theta, cosine of 2 theta, cosine of 4 theta. It doesn't really matter. Then you get 2n leaves. You get double that many leaves. Here you get 4 leaves. Here you get 8 leaves. Leaves or petals, depending what you want to call it, you know? Well, I'll show you how that plays. Well, let's start with the most basic. R equal 3. Now, I could convert that. And how is that? I know that x squared plus y squared equal r squared. That means x squared plus y squared equal 3 squared. I know that's a circle centered at the origin with a radius of 3. Right? But converting is not the way to go. I see r equal a number. I should know it's a circle. Keep in mind, r is positive or negative makes no difference. When I see something like this and I'm not sure what that looked like, so we're going to only do that for the first couple of problems. And then after that, here I have no idea what that looked like. I'll say, look, I don't know what that is, but that's 1 over the cosine of theta. That's r cosine of theta equal 1. But I know what that is. That's x equal 1. X equal 1, look at the rectangular coordinate. I know what that looked like. That is a vertical line right there. And that's what the graph of r equals secant of theta look like. Now, I could plot points and show you how that works, meaning at 0, I'll show you really quick, r and theta. And I could do that here too, right? If theta equals 0, I am right here. If theta equals pi over 4, I'm right there. Pi over 6, pi over 3. And if I trace along, I'll get all of it. Here, if r equals 0, if theta equals 0, secant of 0 is 1, I'm right there. If you go to pi over 4, that's radical 2. There's pi over 4. Radical 2 is 1.4. And you could trace all of these points. And that's how it works. Now we get to this part. Now, I should know how this graph looks. R equals 6 cosine of theta. I should know that that's a graph wrapped around the positive x-axis with a diameter of 6. But let's say we didn't know that. Now, I definitely need another video for this. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me do the first graph and then move on. So here, what I do, I say, okay, let's look at the graph of r equals 6. So the way it works, I'm gonna go 6 above and 6 below, right? Let me lift that one up. I don't know why I have it lowered. There. So, okay. Let's go that way. I'm gonna move 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I would label those clearly. If you need graphing of those, again, I suggest you go to my Math 8 or trigonometry and make sure you get these graphs out of the way. Cosine starts at the amplitude, runs down to the amplitude and back to the starting point. Oh, I know. I thickened that. I wanted that for a reason in my other class. It shouldn't be this thick. So the graph looks like this. This is 2 pi. This is pi. This is pi over 2. And this is 3 pi over 2. Well, let's see how this works. Let's talk about this first piece. This first piece starts at 0. I am at 6. This is 0. Let's say this is 2, 4, 6. I'm right there. It decreases. By the time I reach pi over 2, I am at 0. Pi over 2. If it increases, it goes outwards. If it decreases, it goes inwards. Now, keep in mind, by the time I reach pi over 2, I am at 0. So this is going to come out, start at 6, and it's going to shrink down until you get 0. Now, this piece, starting at pi over 2, 0, this is going to decrease. R is negative. By the time I reach pi, I am at negative 6. Now, if R is positive, I'm in this quadrant. But if R is negative, remember 2 or 4. So it's going to be negative tracing. By the time I reach pi, there's pi, I am at negative 6. Pi, negative 2, negative 4, negative 6. It's very crucial for calculus for you to figure out that between 0 and pi, I was able to trace the whole graph. If you decided to go on, you start retracing this graph. And why is it very important, do you think, to know? Because we're going to find the area of this in the next section. I want to make sure that I run from 0 to pi to trace that circle exactly once. I don't want to find double the area. I want to find a single area. So the graph is a must. I'm going to stop here on this video, and I'll get another video going